So this is the first question. An engineer comes up with two different models for the same dataset. The performances of these two models on the training dataset and test dataset are as follows, right? For model 1, the training error is 0.9 and the test error is 0.1, right? And for model 2, the training error is 0.1 but the test error is 10, right? Now here, uh, see, uh, the performance of a model essentially depends on two factors, right? One is how it performs in the training dataset, and it also depends on how it performs in the test dataset. So let me draw a diagram which depicts how the training error and test error changes when we train the model uh, to a greater extent, or you can alternatively say that we increase the complexity of the model, right? So now if I take this particular graph, so let me say that on the x-axis I have the complexity of the model, right? Or I can say that it is uh, the the extent of training, right? Extent of training, which also indicates how much dependent the model is on the training data set. And on the y-axis we have the error, right? Then this particular line represents the training error, okay? Training error. And the training error always decreases when you increase the complexity of the model, right? And let this line represent the test error. Now we know that typically we want this to be, you know, where the test error is minimum and the training error is also relatively low. This is the optimal complexity for the model, right? Or the model which has this uh, training error and test error is the best fit, right? Now what is the case given in the example, right? So in the first case the training error is around 0.9 and the test error is 0.1, right? Which means that the test error is around, so you can say that the test error is 1 by 9th of training error. And definitely, so what does that mean? That means the model generalizes well, or you can also say the model performs well on unseen data. So this is the data that the model has not seen during training, right? But what about the second one, right? In the second model, model 2, so this is model 1, and in model 2 the test error is 100 times of training error. This means the model does not generalize well, right? Because when it looks at unseen data, it performs poorly, right? So poor performance in unseen data. So this is the difference between model 1 and model 2. And definitely now if you compare the training error of model 1 and model 2, they are not that bad, okay? Both of them are cool enough. So we would go with the model 1 because this generalizes well to the unseen data, right? So here we have the second question. Consider a model H for a given d-dimensional training data points x1, x2 up to xn, right? And the labels are also given y1, y2 up to yn, right? Now, this is a special scenario where what you do is that all of your prediction is nothing but y bar, right? This is known as the naive estimator. Okay, this is also known as the naive estimator, right? What it does is that irrespective of the data point, it will just output the average of the output labels in the training data set, right? Now the question is, which of the following error functions will always give the zero training error for the above model, right? Obviously, so we want this to be zero always, right? Which means, what does that mean? That means that uh, so let's look at the first one, right? The first one says h xi minus yi whole square. That is a training error. In the second one we have a mod. In the third one we do not have anything. It's just summation of hxi minus yi, and in the last one we have a cube, right? What is to be observed is that since hxi is equal to y bar, right? Now this holds for every xi, right? So this should hold for every xi in the data set. What is, so let me write it d, and then in suffix let me write train. So what is the train? D-train is the data set that has been used to train the model. And what are those data points? x1, x2 up to xn, right? Now hxi is equal to y bar every time, and I can write y bar to be n times of summation yi, or sorry, I can write it as summation yi divided by n, right? Now this means that if I, so this should hold for every element in D train, right? So if I take the sum of all hxi, right, where xi belongs to D train, right, that would be nothing but n times y bar, right? And what is n times y bar? That is again summation of yi, where yi is all those data set in D train, right? Now that means that if you take the sum, right, of all I in the training data set, okay, right, and you take hxi minus yi, this will be equal to 0, right? This is exactly what is given in the third option, right? So this is the correct answer, right? Another way to look at it is that since hxi is equal to y bar for every data point, so this should be equal to summation of y bar minus yi whole square, right? Which is nothing but the variance of sigma square of y, right? Now this is always non-negative, but it need not be 0, right? Similarly, in this one we have that summation y bar minus yi. Again, this is non-zero, but this need not be 0 always, okay? In the last option we can say that this would be y bar minus yi whole cube summation. Again, this can be negative or positive or 0, right? But need not be 0 always. But for the third option, this would be summation of y bar minus yi, which is equal to n times y bar minus summation of yi, right? Now y bar can be written as summation yi by n minus summation yi, which is equal to 0. So in the third example we are getting a mandatory 0, and in other examples we are getting that it should be non-negative, but it need not be 0. So this is the third and the fourth question. So we are given a data set of one variable and one output. Okay, and it says we want to fit a linear regression model of the form yi equal to w transpose xi. Okay, and there is, note that there is no intercept term. Okay, it's just of the form yi equal to w transpose xi, and definitely it says assume that the initial vector weight is w equal to 2. So this is essentially not a vector. Okay, it's just like a scalar, or you can consider it as a 1 by 1 vector, but actually it's a scalar of the form yi equal to w xi, right? And the initial value of w is 2, so we can write w0 equal to 2, right? The question says what will be the weight after one iteration using the gradient descent algorithm assuming squared loss function. Okay, so what is the loss function here? The loss function is given by sum over of wxi minus yi squared, right? And I running from 1 to 3 because there are 3 data points, right? Let me call this f. In this case, what will be the gradient of f? The gradient of f would be 2 times summation I running from 1 to 3 xi times wxi minus yi. And definitely what we are taking gradient with respect to w. Okay, so we are taking derivative with respect to w. Since w is just a scalar in this case, we can also write this as df upon dw. Okay, now what does the gradient descent algorithm say? The gradient descent algorithm says you start with some w0, then given wk you have to update wk plus 1, which is the k plus 1th iteration, that is given by wk minus some learning rate, which is, so the learning rate is also given. It says the learning rate is eta equal to 1, so minus eta times the gradient of f, right? So this is the gradient descent algorithm, right? It's very straightforward. So this is the initialization step, right? Initialization, and then the second step is the update step, right, where you update the parameter w, right? So what we need to do, since w0 is given, right, what will be the first iteration of w? That would be w0 minus eta times grad f. Now it's not just grad f, it's grad f evaluated at w0, right? Or let me write it here, grad f evaluated at wk. So we need to use the value of the kth iteration, the parameter value obtained at the kth iteration, in order to compute the k plus 1th iteration. That is the point. So this is gradient f evaluated at wk. Now, so now we know w0, that is 2, minus eta is 1, it's given, and the gradient of f is given by 2 times of xi into wxi minus yi, right? So we need to compute that. So again, in this case will be used, so what will be w0 times x? It would be, or x1, that would be equal to 2 into minus 1 minus 2, 0, and then 2, right? Then what would be w0 x1 minus y1? This would be minus 7. This is also minus 7. This is minus 4, right? So small part of the computation was missed. We also need to compute what is x1 times w0 x1 minus y1, right? Let me just erase this part. Now we can write this as 7, this would be 0, and this would be minus 4, right? So we have 2 minus 1 times of 2 times of 7 minus 4, which is nothing but 2 minus 2 into 3 is equal to minus 4. So minus 4 is the first iteration of W, right? Now the second question or the fourth question says that if we stop the algorithm at the weight calculated in question 1, I think they're referring to question 3, what will be the prediction for the data point x1 equal to minus 2? Again, the prediction is given by W transpose X, right? Here W is a scalar, so the prediction can be written as minus 4 times minus 2, which is equal to 8. So 8 is the prediction. So the fifth question here is about stochastic gradient descent, right? This is a variation of the gradient descent, and it is used particularly in settings when the data set is very large, right? Data set is very large. So the issue here is that typically the gradient is given by, so when we have the gradient of f, when f is the, let me write, the gradient of f will be 2 times of xx transpose times w minus x times y, 2 times x times y, right? This will be the gradient when we take f to be equal to x transpose y, sorry, x transpose w minus y norm squared, right? Or alternatively, you can write this as x transpose w minus y whole transpose x transpose w minus y, right? Now, what happens is that when the data set is very large, computing the gradient of f, because it has an xx transpose component, computing this is very data intensive, right? So what we do is that instead of the gradient descent, we have a different algorithm. It's a modification of the gradient descent, where we start with an initial parameter. So this is the initialization, and then the update goes on like this: wk plus 1, the k plus 1th iteration is nothing but the kth iteration minus uh, some some learning rate, let me call that eta times, we compute the gradient for fi at wk. Now what is fi? So fi is the error component corresponding to the ith ith data point, right? So this is the error of the ith data point. Now what does that mean? See, what is f? F is nothing but, f can be alternatively written as summation of x transpose or xi transpose w minus yi squared, I running from 1 to n, right? Now and the ith error would be, so fi would be equal to, there will be no sum, it will just be xi transpose w minus yi whole squared, and therefore the gradient of this would be equal to 2 times of xi multiplied by, or you can say xi transpose w minus yi, right? So or in fact you can write this as, so the gradient would be equal to 2 times of okay, so yi is of dimension n by 1, right? Or no, all of them are scalars, so only x, so yi's are all scalars, right? And xi transpose W is a scalar, right? So what we have to do, so the gradient of Fi is given by 2 times of xi transpose W minus yi multiplied by xi, right? So this is actually a vector, and this is the scalar component, and this is the vector component, right? So now what happens is that now we can always say that, so what is, so and what happens, and the third step is obtain. So since we are running capital T many iterations in the question, so after running T iterations, we will use the average of all W's. What does that mean? We will be using W bar equal to 1 by T times W I running from 1 to capital T, right? So essentially this means that we'll compute it for each data point separately, and then we will average them, okay? And the data point I is chosen randomly, okay? So let me write that. Note, the ith data point is chosen randomly. In fact each, it is chosen in such a way that each data point has an equal chance of getting chosen, right? And you can say uniform, or you can say with uniform probability, okay? With uniform probability, right? So the final weight after capital T many iterations will be nothing but the average of all the weights that are obtained in the process. Alright, so here we have a problem on kernel regression with a polynomial kernel of degree 2, right? Now what does this mean? This means that the kernel of x comma y is given by 1 plus x transpose y whole square, right? This is by definition the polynomial kernel of degree 2, okay? It's applied on a data set x and y, and the weight vector is given to be w equals x times something, right? Now let me call this alpha, this vector. In fact, this should be the transpose of this. It should be a column vector, okay? So just to recall, x is of the form x1, x2, and so on, xn. There are n data points, so this is an n by d matrix. Sorry, this is a d by n matrix. There are, so because each xi belongs to capital R D, right? And we know that the weight vector, which is the optimum weight by which is obtained by minimizing the loss function or the objective function, this can be expressed as a linear combination of the data points, right? So we can write it as x into alpha, right? Here x is not given, but alpha is given to be 0.3, 1.6, 4.2, minus 0.5, and 0.9. Now the first question is, what is the significance of alpha, right? So we can say, so how many data points are there first of all? So the number of data points in x are 5, right? Why? Because alpha is of size 5. So alpha always lies in Rn, where n is the number of data points, and we know that alpha is a 5 cross 1 matrix or a column vector, so n is equal to 5. There are 5 data points, but we do not know the data points, right? First of all, let's see what is the interpretation of alpha, right? Interpretation of alpha. So alpha is a vector, so let me say alpha I corresponds to the ith data point, okay? Now since w is a linear combination of the data points, alpha I represents the importance of the ith data point in the determination of W. So you can say that alpha I denotes the importance or weightage of the ith data point in the determination of W, right? The weight vector, right? So this is the interpretation of alpha I, right? So you can say that W is nothing but alpha 1 W, sorry, alpha 1 x1 plus alpha 2 x2, right? So on up to alpha n xn, right? And this is how the importance interpretation comes up, right? So the first question is, which data point plays the most important role in predicting the outcome of an unseen data point, right? So obviously we know it is this one. So the answer would be I equal to 3, because this is the this is the largest in magnitude, right? So the most important one, the most important alpha I is nothing but that I, or you can say k equals to arg max over I modulus of alpha I, right? So we will be looking at the absolute value, right? And here in absolute value 4.2 is the largest, right? So the third data point is contributing the maximum to the determination of W, right? Again, W is also something which we do not know yet, right? At the same time, we can also observe that the least important one is, so the least important is the first data point, Why is that the case? Because alpha 1 is equal to 0.3, which is of minimum magnitude, right? Alright, so now we need to make a prediction, right? So the question says, what will be the prediction for the data point? All of them are 0, right? So how to obtain a prediction for in case of a kernel regression has been extensively discussed in one of the practice assignment videos. One can check it out, where the theory is extensively discussed. So here let's see how to determine the prediction, right? The prediction for, there are 5 zeros, okay? This is what we want to predict. So the step 1 is that we need to compute the kernel of xi, which is the ith data point, with the new data point. So let me say x new, right? And this will be nothing but 1 plus xi transpose x new whole square, right? Now since x new all of them are 0, this is nothing but 1 square, right? So this is 1 square for every xi, right? I running from 1 to 5, because there are 5 data points, right? Now all of them are 1, okay? The second step is we need to take the dot product of this along with alphas, right? So it will be 1 1 1 1 1. This 5 1 corresponds to the 5 different kernels that have been obtained, and that will be dotted with alpha, which is 0.3, 1.6, 4.2, minus 0.5 and 0.9. So this will be equal to 0.3 plus 1.6 plus 4.2 minus 0.5 plus 0.9, which will turn out to be 6.5. This is the prediction of the 0 vector, right? So this is the prediction corresponding to 0, all of them are 0. So here we have the question where it says if W star is the solution of the optimization problem of the linear regression model. What does that mean? That means that W star is nothing but argmin of summation argmin over W summation W transpose xi minus yi whole square, right? Now in matrix format you can write it as argmin of W uh, summation, or instead of this we can write x transpose W minus y, right, norm squared, okay, norm squared. Or equivalently we can write this as x transpose W minus y transpose x transpose W minus y, right? So these are all three same expressions, right? And what was the idea we followed? We said that we will first take the first derivative with respect to W and then set it equal to 0, right? So if I expand this term, I would get W transpose uh, x transpose W, right? And then I'll get a minus y transpose x transpose W, right? And then I would have a minus of W transpose xy, and then minus or plus of y transpose y. So this is my objective function, right? Let me write this as f, which is a function of W. Now if I take the gradient of f with respect to W, I would have 2 times of xx transpose W minus this would be xy, and there would be 2 times of xy, right? And what we do, we set this equal to 0, right? So what does this mean? This means that xx transpose W minus xy is equal to 0. Now observe that we have some similar expression in one of the options. To obtain that, what we have to do is multiply on the left by W transpose, right? So that would give us W transpose xx transpose W minus W transpose xy is equal to 0, right? Now so this can be written as, so this means that uh, so what we can do is that here we have a W transpose x, we have a W transpose x here as well. So that can be written as xw or x transpose W whole transpose, right? And the remaining can be written as x transpose W minus y. This is equal to 0, right? Now this is same as saying x transpose W minus y, sorry, x transpose W minus y whole transpose into x transpose W is equal to 0, right? So this is one of the conditions that W has to satisfy in order to be the minimizer of the objective function, which means the W star will also satisfy this equation, right? So let me call this 1. And since W star satisfies this condition, we can say that the second option is true, right? But what about the other options, right? Let's look at the third one. The third one says x transpose W star into x transpose W star is 0. But there is some inconsistency here. The dimension of x transpose is n cross d. The dimension of W star is again d cross 1. Again, x transpose is n cross d, and this is d cross 1, right? So this term is n cross 1 and this term is n cross 1, which means the matrix multiplication is not compatible, right? Because for a matrix multiplication to be compatible, the number of columns in the first matrix should be equal to the number of rows in the second matrix, right? Which is not the case here, right? So that's why this option is definitely false, okay? Now if you look at the last option, it says that y is exactly equal to x transpose W star, right? Now this will happen only if the line passes through, so this will happen only if the line passes through every data point, right? through every data point xi comma yi, which is definitely not always the case, right? So this is also not true always, right? Because the question asks which of the following expression is always correct. Now, what about the first one? The first one says that y transpose of x transpose w star is 0, right? Again, this is also not true always, right? To see this, let's consider a simple linear regression problem, okay? A very simple one. You have 1 comma 1 and say 2 comma 2, right? 2 comma 2. So the regression line will definitely pass through both these points, and it will also pass through 0, right? Now, what is y here? Y is nothing but 1 comma 2, the 1 2 vector, right? And what is x? X is also 1 2, and w is a scalar which is 1. W star is a scalar which is 1, right? Now if I do w transpose x transpose w star, I would get 1 square plus 2 square, which is equal to 5. That's definitely not 0, right? So this is definitely not the case. The first option is definitely false, right? Now, with regards to the second option, there is a very important interpretation to be made. The interpretation is that uh, when we say that y minus x transpose w so the transpose of this times x transpose w star, let me write w star, is equal to 0. What does that mean? That means this guy is perpendicular to this guy, right? But what is this guy? This guy is the error vector. And what is this guy? The second term is nothing but the prediction vector. So it says that the error is perpendicular to the predictions. Now the error vector, let me call that E, is actually a member of Rn, and the prediction vector, let me call that P, is also a member of Rn. Okay, so Rn is the number of data points, okay, right? So this is a very important property of linear regression, that the error vector is perpendicular or orthogonal to the predictions vector. So here we have a question which says the gradient descent with a constant learning rate of eta equal to 1 for a convex function starts oscillating around the local minima, right? What should be the ideal response in this case, right? Either increase or decrease the value of eta, right? So before that, let's have a few points about the learning parameter or the learning rate. So if eta is large, right, then it is possible that it does not converge, right? The algorithm, which algorithm? The gradient descent algorithm might not converge. Why it does not converge? I have explained that in another video which talks about the convergence of gradient descent, where we see that for a particular condition or a particular inequality to hold, we require eta to be less than equal to 1 by L. What is L? L is a Lipschitz constant, because we are assuming that the gradient of f is Lipschitz continuous, right? So L is the Lipschitz constant associated with that, with the gradient of f, and we need eta to be less than equal to 1 by L. Only then we can assure convergence, right? So this is one of the important conditions. So if eta is greater than 1 by L, the algorithm might not converge. So this is the informal way of saying this, is that if eta is quite large, the algorithm might not converge, which means that the function, which means that it oscillates around the minima. Similarly, if eta is small, very small, then it might take longer it might take a long time to converge, right? Right. So these are two important points about the learning rate. So with the first point we can conclude that if it is oscillating around the local minima, right, then we need to decrease the value of eta, right? So one pictorial way of seeing it is that suppose this is a convex function, right, and we start here, right, and if the step size is very large, okay, say for example the step size uh, crosses uh, this range, right, so the next step size would be here, which means it will take a value here, and then it goes again to the left, right, and then it goes again to the right. So essentially what happens is that instead of converging, it keeps on oscillating between around the local minima instead of actually going down, right? Whereas if eta is small, then we can assure that the direction is small, so it will move slowly towards the minima, right? This is a pictorial representation of why this might work. So here the question is, uh, if the error in the linear regression model is assumed to have constant variance. This is true because one of the critical assumptions of a linear regression model is that of homoscedasticity, right? Homoscedasticity. What does that mean? That means that the errors, so this means that the errors have constant variance, right? Right. Now, theoretically, we say that y is equal to beta x plus epsilon, and epsilon is technically assumed to be normally distributed with mean 0 and variance sigma square, right? So sigma square is a constant and does not depend on the data points, right? So that statement is true, right? Let's so suppose that it does not have a constant variance, right? Then how would the data points look like, right? So suppose it's not, so this is a case of not having constant variance, right? It's a pictorial representation. So let me say this is x and this is the target y, right? And suppose we have points like this, right? So what is happening essentially is that at each point of x, right, the variability of the points which are corresponding to that x is not really constant, right? At some point it's smaller and at some point this is larger, right? And this is one of the very naive pictorial representation of how a non-homoscedastic or a heteroscedastic data will look like, okay?